Good evening, everyone. In this video, I will do topic modeling with BERT-based sentence transformer model. And also at the end, for labeling the topics, I will implement a particular technique called automatic cluster labeling, which was proposed in a paper in 2021, where I will concatenate the most common verb, direct objects, and top two nouns from each text cluster for labeling the topics under the techniques as proposed by this paper. It will be a long coding session, so be patient, and of course I will put the link of the source code in the description of the video. And for the data set for this project, I'm going to use this one. It's pretty popular and pretty large real world data set called Steam Review Dataset, and the dataset contains over 6.4 million publicly available reviews in English from Steam Reviews portion of Steam Store run by Valve. Each review is described by review text, the ID of game it belongs to, review sentiment, positive or negative, and a number of users who thought review was helpful. This is essentially an extension to previously released Team Review dataset. The resource is provided. All right, so this is the source of the dataset. I will put the link of this in the description as well, so you can download it in your local machine or your cloud machine. All right, with that, let's get started. So I have already downloaded this dataset in my local machine. And that's why I'm referring to the CSV file. It's a single CSV file of 2 GB, 2 gigabyte, quite large file. And this is here. I'm reading the dataset with pandas, and look at the particular way I'm reading it here with a lambda function with skip rows, because it's a large dataset, and for the purpose of running this notebook relatively quicker, I'm only reading by randomly selecting 0.4% of the rows. So my p-value here is 0.004, and then with the lambda function, all I'm doing is that if I greater than 0 and rn.random greater than these p-values, only those rows I'm reading into pandas. And let's run it. Even 0.4% of the dataset, taking a little bit of time. Yeah, so this is I'm just printing the dataset dfreviews.head here, and you can see that I have the app ID, app name, and review text, review score, review votes. So for the purpose of this exercise, where I'm going to do topic modeling on the actual reviews, the two most important columns that I will be working with for almost all the notebook is these two: review text and review score. So review text has all the entire review, and review score is just two numbers, so there's 1 and -1. Let's do a quick count plot to check the count of the dataset. Yeah, so I have -1 and 1, and note that here we are referring to only 0.4% of the dataset. So this distribution may not be representative of the whole dataset, but I just wanted to quickly check here. Okay, now convert some basic pre-processing. Let's quickly do. So first I'm converting the review text to string. Similarly, review votes. And also, let's strip all the extra spaces, df. Review text. And I'm also going to drop the reviews with null score. So let's define a new data frame name. Actually, it will be score. And finally, I want to change the scores from 1 and -1 sorry, from 1 and -1 to 1 and 0, just to be consistent with the regular machine learning projects numerical values, because here -1 actually represents 0. So I have this binary representation of the review score. All right. Yeah, okay, some basic pre-processing was done. And now I am going to do a word cloud. The word cloud, I personally don't get much information from the word cloud generally, but just to quickly see, I normally sometimes do word cloud, but it doesn't have too much of informational power indeed. Review for reviews. I can actually do reviews too. We already imported this word cloud module at the very top, so now I can just pass the configuration. Oops, sorry. Background color. Maybe do 700. Bilinear. A max font size. Oh yeah, I missed the comma. Okay, it is building the word cloud, and that's my word cloud. And obviously, as you can expect, game, early access, review. These are kind of big words. Okay, now let's move on to do some more data preprocessing. Let's remove a few of the column in review text has early access review comments. Let's remove them because these are reviews with no comments written by a human or human reviewer. So I'm going to just remove those columns. Not equal to review. And also I'm going to review from the review text column all the nan not a number of values. So I'm going to make use of the tilde operator here. This tilde operator works as a not operator in this scenario. So df is in now let's check the shape of, and also drop duplicates if there is any. So what happened? Didn't I run the previous cells? I think I did not run the previous cells. Let's just restart and run everything previous. Okay, I got the result here. Next, just quickly check the head of this data frame. Alright, now that's how the data frame is looking like right now. And I found that all of the F words and similar words such as shit, etc. are replaced by multiple these emoticon, love emoticon in the original text, and this is a source of confusion to the model that we are going to use to get the text embeddings. This symbol, that is this heart symbol, is a symbol of love, while they appear in the negative comments, and therefore it will impact our classifier. So I'm going to replace them with 4 asterisks, which seems token close to the F words. So let's do that. Define a util function, and for my next few preprocessing, I'm going to define quite a few util function and apply them one by one on the data frame. So this will do a substitution, return the string obtained by replacing the leftmost non-overlapping occurrences of the pattern in a string by the replacement. REPL can be either a string or a callable. If a string / escapes in it are processed, if it is callable, it's passed the match object and must return a replacement string to be used. Okay. So the first argument needs to be the one that is going to be replaced. So I'm just going to kind of copy it from here. Can I do that? Yep. Okay, that's my first argument. And I'm going to replace it with okay. Okay, so that's my first util function. And next function I have is for to remove all the emojis. So for removing all the emojis, I have a util function. I'm just copying it from my source. Yeah. So this is just using this regex pattern to substitute those emojis. And that's pretty much it. So the first is for emoticon, the second is for symbols and pictographs, third is for transport and map symbols, and the last is for flags in iOS. Okay, now I need to do some more cleaning of some basic characters. Again, I'm going to use this re.sub with regex pattern, and this will, as probably it's very clear that for example this regex it will remove the greater than sign. The first one will remove the hyperlinks and markup and so on. And now I need to remove numeric characters. So let's define digit character, so \d plus with an empty space, with actually nothing, text. And the next one is a function to remove function to unify white spaces. So unify white spaces, and alright, and then I need another function to remove symbols. Okay, next one, another util function to remove punctuation. Dot join. Within the not in, I have to pass all the punctuations. So I have I want to include question mark, period sign, comma, then slice notation, all of them. Okay. Cool. And now I need to remove stop words. And for that, I am going to use nltk.corpus stop words, all these standard modules. Stop words dot words. So I already downloaded porter stemmer. Yeah. And also I need to define lemma. Word lematizer. And now to remove the stop words, another util function. Word. Cool. And next is function to use stemming to normalize words. So I need to get nltk.corpus and then snowball stemmer. So now you have to get each of the words from this word tokens variable and stem it. So I'm going to use this. Okay, and now finally I'm ready to apply all the cleaning util or pre-processing util methods on my data frames, a particular column. So another util function which will take the data frame and a column name, and quickly check what was the status of our data frame. Okay, so it has got review text, and this is a column that I want to clean. But for the clean column, I will create a new column names. I'm going to create a new column named cleaned review text. Okay. So I'm just first I don't want to touch the original df, so let's create a copy. And here is where I'm creating a new column from the original data frames, and the original data frames column name was review text. And now this is where I'm going to apply all my preprocessing util methods. Actually, let's name it preprocessed. Oh, okay, df processed is just fine. Next method will be replace hearts with pad. Actually, here I wanted to do this. Okay. Remove punctuation. Unify white spaces. Here, they were all. And the new column name that I am going to give to the clean column is review text clean. All right. So now I'm just printing the head after doing all these cleaning. Yep. So now we can see we have these new column review text clean, and we can see all these oh, something is wrong. These hearts were not replaced with 4 stars. Let me fix what happened. And I figured that this remove symbol, this method over here, remove symbol, that's actually replacing those asterisk symbols, star signs. So for now I'm just commenting out these remove symbols. Just let me just delete this line. Yeah, I do not want that remove symbol method, so I can keep these asterisks instead of the heart symbols, because this kind of is meaningful to the model. Okay, let me remove this and remove that. Okay. All right, so now that's a situation the structure of our data frame. And from now onwards, we can kind of forget about this review text, because this is the original review text that was there. We will work only with this review text clean, this column, because that's a pre-processed text. Okay, now let's select around 2000 negative samples randomly, using if you want to use more data, definitely you should use it, but I just wanted to run this notebook while recording, and that's why I'm choosing 2000. But definitely for real world cases, if you can, select the whole data set. So DF processed. So I'm selecting those review text clean as a list, and now I'm going to print this negative reviews dot web. Yeah, makes sense. And I'm also going to check out the head. Yeah, all looks fine. So this is my all intents. So the all intents is coming from this line here. It's a huge list because it has all the text from my review text clean, that is this column. Okay, so this one I just wanted to check, but I can just clear the cell output here for now. Okay, now I am going to split the comments or reviews into sentences, and because some of the Steam reviews are very lengthy, it is not surprising to see multiple topics in one reviews, and that's why some of them are really lengthy. If we pass the whole lengthy comments through a sentence encoder, we will not see a nice and clean clustering outcome, and hence I am going to ignore these noises and less important sentences by splitting the reviews into many sentences. So what I do is, and what I'm going to do here is to remove the noises, is to include only the sentences with more than 4 words. You can do with 5 or 6 words as well, to play around to see what gives you the best result. So I'm going with 4. I'm tokenizing these individual intent. All sense dot. Start. I'm updating the all intent to be equal to all sense. That is len. Okay. Next, now I'm ready to pre-processing is almost done. It's actually done. So now I will bring in sentence transformer and do my sentence embedding. Okay, so here there are quite a few models that you can use with sentence transformer, and the one that I'm going to use is called all MPNet base v2, and you can check their Hugging Face page to know more about the model. And actually, that all MPNet base v2 is a sentence transformer model which maps the sentence and paragraphs to a 768 dimensional dense vector space, and normally are mostly used for tasks like clustering and semantic search. So that's what I am going to use. Small util function here for embedding. And also, I think I already mentioned in the first part of the video that I referred to a very popular blog, which the description of which I will give in the code in this notebook. And in that blog as well, they used I think all MPNet base v2. So I got guidance from that blog as well, but for this model choice. In that case, embeddings will be in yes. Oops, sorry. This is double equal. Sentence. So the name of the model is all MPNet base v2. And remember that in sentence transformer, right now I'm not using the GPU, and I'm not going to use a GPU, and in that case I have to mention the device as equal to CPU. Otherwise, by default, that is, if I do not mention the device argument here in this line, then by default it will try to use the GPU. So I am going to mention device equal to embeddings st1 will be st1. So I can just copy this thing from here. All intents. All right, now running this cell will take 3-4 minutes, but let's just start the running. And after the model inferencing was over, I get this embedding underscore st1 as the output from the model, the embedded vector. And here I print the shape, and we can see it has 2000 rows, 768 columns, that is 768 features, you can say. It's a vector. And so now, and this is expected because, as we discussed, this all MPNet base v2 model, as was clearly mentioned in Hugging Face official model card documentation, that it produces a 768 dimensional vector. And hence, now the next question is, how do we reduce this dimension? Because here the purpose of this exercise is to do topic modeling. And if it was for some other purpose, for example, text generation or question answer generation, etc., those are different motivation where dimensionality reduction may not always be very important. But here in this case, dimensionality reduction is important indeed. So for cases like topic modeling, it is recommended to reduce the dimension of sentence embeddings into smaller dimensions before performing clustering. For more details, you can check some of the papers in this space. And the method that I'm going to use is HDBSCAN. It's a super popular dimensionality reduction method. Which has benefits to the topic modeling. It has some features like the probability score that help us to automate the optimum number of clusters, which is a big trouble in an unsupervised topic modeling. Now, before going into more details on the HDBSCAN, a few more quick words on the dimensionality reduction case here. So a manifestation of the curse of dimensionality is that distance measures such as Euclidean and Manhattan needed for clustering become meaningless at very high dimension. Here in this case, our dimension is more than 500, 768. So at this high dimension, those distance metric becomes kind of meaningless. Now, while some of the sentence transformer pre-trained models were created in a way to preserve the usefulness of some distance measures, dimensionality reduction before clustering will still greatly improve your result. To prove this to myself, I briefly explored using different clustering algorithms and embeddings without dimensionality reduction first, and I got kind of worse results. So, and here I'm going to first implement UMAP, or Uniform Manifold Approximation and Projection for Dimension Reduction, which was introduced in 2020 and has quickly grown in popularity as a very popular dimensionality reduction technique. UMAP is much faster and more scalable than TSNE, while also preserving the global structures of the data much better. This makes it useful for both visualization and as a pre-processing dimensionality reduction step to use before your clustering. So let's start using that. And now I'm just going to import all the libraries for dimensionality reduction and also for clustering. And they are these. So UMAP here is for the, as we just discussed, it's for dimensionality reduction, HDBSCAN for clustering, and I'm also importing this Hyperopt. We are going to discuss about this Hyperopt in a moment, but just know for now that this is a super popular package to handle Bayesian optimization for searching the optimal hyperparameters. Alright, now few words on HDBSCAN, our clustering algorithm of choice. And this is indeed one of the most sophisticated algorithm used in many projects. So a cluster analysis is the task of arranging a set of similar data points into groups. It is an unsupervised machine learning task that can discover patterns or identify related groups from a dataset. There are many different algorithms proposed for cluster analysis. The one and the most common one that you probably will see if you do search for, and this is rather classical or traditional algorithm, which is k-means. So the k-means algorithm is commonly used for clustering since it is fast and easy to understand. However, there are some potential problems with this algorithm. First, the number of clusters or partitions need to be provided as input to the algorithm. Number of clusters that may be present in a new dataset is, however, not always known. So you have to put a number based on your assumption. Another problem with k-means is that k-means is more of a partitioning algorithm than a clustering algorithm, since it partitions all the data into groups by minimizing the distances between data points. These problems are also existent in other clustering algorithms. For example, the affinity propagation and spectral clustering algorithm are partition they partition all the data into groups, so even outliers or noisy data points are included in the cluster. Another well-known algorithm is agglomerative clustering, which, like k-means, requires a number of clusters to be provided as an input to the algorithm when a threshold parameter is not used. So these were the original some of the issues and problems with the traditional algorithm, and that's where HDBSCAN comes into the scene to solve some of them. So the HDBSCAN clustering algorithm is a density based algorithm. Unlike k-means, it does not require that every data point is assigned to a cluster, since it identifies dense clusters. Points not assigned to a cluster are considered as outliers or noise. For our current exercise here in this video, it is preferable to use an algorithm that does not require specifying the number of cluster upfront and can also tolerate some noisy data. So that's where our solution depends on HDBSCAN. Because density based algorithms, which is what HDBSCAN is, they are a good option here, as they do not require specifying the number of clusters and are indifferent to cluster shape. So I use HDBSCAN here. The full form of HDBSCAN is hierarchical density based spatial clustering of applications with noise, and they have this has become the most popular since it has fewer and more intuitive hyperparameters than DBSCAN and these robust to variable density clusters. The HDBSCAN documentation provides a very helpful comparison of different clustering algorithm. I definitely suggest you go through them to understand it more better way. All right, with that, let's start with implementing HDBSCAN for creating or generating our clusters. Number of neighbors, NEIGHBORS. So I definitely suggest going through the documentation to understand and making sense of these arguments. The documentation is very well explained indeed. Am I spelling it correct? NEI. Yeah, there's a mistake. NEIGH. Sorry. Yeah. Next is number of components. So the what these function will do is that it will return the HDBSCAN object of clusters, meaning this function returns HDBSCAN objects after first performing dimensionality reductions using UMAP, which I'm going to include in a second. And in terms of the arguments, the first one, message embedding, this is the embedding to use. Then in neighbors is the it's an hyperparameter for UMAP. Also in number of components, that's also for UMAP, which is a hyperparameter. Mean cluster size, this is for HDBSCAN, that is the hyperparameter for HDBSCAN, and also mean sample and random state. So first I am going to generate a UMAP embedding. UMAP, and that will take all these arguments. In neighbors will be in neighbors, cosine distance. Yeah, looks all right. And to that, I need to apply the fit transform. Actually, let's take all these util function to a separate util.py file, because otherwise this main Jupyter notebook will become too much noisy. So I'm just going to cut it from here. This is my utils Python file. Yeah, it looks better and clean. All right, so my UMap embeddings, DRANS transform. This spell checking, yeah, quick fix, add UMap, okay. Alright, so my UMap embeddings are ready. Now next thing, I need the clusters from HDBSCAN. And here again, I need mean cluster size equal to samples. Metric, I'm choosing here Euclidean. Gen mean space tree. Yeah, let it become true. Cluster selection method. That for me is EOM. So this cluster is going to fit my earlier defined UMap embeddings. Yeah. Okay, this function is done. Yeah, and now I'm going to use this package HyperOpt, and so let's quickly see what is HyperOpt actually. So HyperOpt is an open source Python library created by James Bergstra in 2011. HyperOpt is a tool that allows the automation of the search for the optimal hyperparameters of a machine learning model, and it's based on Bayesian optimization supported by SMBO methodology adopted to work with different algorithms such as tree of Pearson estimators, that is TPE, and also adaptive tree of Pearson estimators, that is ATPE, and lastly the Gaussian process GP. So the approach of Bayesian optimization focuses on a probability model, that is a probability of a score given a configuration, this kind of thing, which is updated through an iterative process of querying a history age whose objective is the maximization of the score given a configuration. So HyperOpt takes Bayesian optimization as its premise by making some variations in the sampling process, the definition, and then narrow down of the search space and the algorithm for maximizing the probability model. So let's start building the basic util function for HyperOpt. Score clusters. So this method will return the label count and cost of a given clustering. And the arguments here are this cluster, which is the return value from the HDBSCAN clustering object, and probability threshold. This is a float number. This represents a probability threshold to use for deciding what cluster labels are considered low confidence. And at the end of the function, it will return a label count and also the cost. Label count will be the number of unique cluster labels, including the noises, and the cost is which is a fraction of data points whose cluster assignments has a probability below the cutoff threshold, which kind of represent the cost of clustering. So first I need cluster labels. Cluster.labels. So these cluster.labels underscore, this syntax is coming from the library itself. So this cluster object knows and stores the result in an attribute named labels underscore. That's what it is. And it is an array with an integer for each data sample. So it just represents an array, something like this. Okay. Yeah. So the samples that are in the same cluster get assigned the same number, and the cluster label starts at 0 and then count up. That's how it works. Cluster labels, and then I need a label count. Cluster labels. Total number will be cluster.labels, and now the cost. Like I said again, that the cost is the fraction of data points whose cluster assignment has a probability below the cutoff threshold. And what is our cutoff threshold? That's this probability threshold, which is equal to 0.05. So I need a conditional statement here, np.count non-zero. Clusters.probabilities is less than the probability threshold, and it needs to be expressed as a fraction of the total number. Okay. So the HDBSCAN library implements soft clustering, where each data point is assigned a cluster membership score ranging from 0.0 to 1.0. That is 0.0 to 1.0. A score of 0.0 represents a sample that is not in the cluster at all. That is, all noise points will get the 0.0 score, while a score of 1.0 represents a sample that is at the heart of the cluster. That's significance of these cluster threshold score. I'm going to return the label count and okay, that's this function is done. I need the next function, which is my objective function for hyperopt. So this objective function is for my package hyperopt, which will be used to get the optimal hyperparameters. And This objective function is part of the kind of recommended way to use hyperopt as mentioned in the documentation. It takes the first argument as param, which is a dict, and that will contain the values for the various configuration part of hyperopt, which is number of neighbors, number of components, minimum cluster size, and random state. So yeah, param, and then embedding. And these embeddings is just the vector embedding of the text, and lower these label lower and label upper, they are the lower end of range of number of expected clusters, and the upper end of range of number of expected cluster respectively. We are going to use this generate cluster that we have defined here. And that takes embeddings, then in neighbors, which will be equal to, I'm going to get it from the param dict. Any IGH. BORS. Next one is actually I should just name this param as S. Oops. Yeah. And this random state is just random state as well. Okay, and next I need label count and cost from my the score cluster method. Probability threshold, I'm passing as 0.05. Cluster, or maybe just add a S to both of them. And now I'm going to add a penalty on the cost function. So this penalty is kind of an extra cost when this is outside of the desired range of groups. So you can choose different numbers. It's kind of an hyperparameter, and I'm choosing 100% penalty on the cost function if outside the desired range of groups. So label count is less than label lower, or penalty equal to 1.0, else And the loss function, the loss value will just be cost plus penalty. Okay, and what I'm going to return from this method is dict status. Okay. All right, so this method is also over, and now my next method is for doing the Bayesian search. And now a quick word on the hyperparameter optimization with Bayesian search. So normally in machine learning, we have these four, the most common technique to do hyperparameter based hyperparameter search, which is manual. Manual is probably never used. Then I have grid search, random search, and lastly Bayesian model based optimization. And this is the one that we are going to use in this project. So in one sentence, the Bayesian hyperparameter optimization is about building a probability model of the objective function and use it to select the most promising hyperparameters to evaluate in the true objective function. So the main difference between Bayesian search and the other method is that the tuning algorithm optimizes its parameter selection in each round according to the previous round score. Thus, instead of randomly choosing the next set of parameters, algorithm optimizes the choice and likely reaches the best parameter set faster than the previous other two methods, that is better than a grid search or random search. Meaning this method, that is a Bayesian method, chooses only the relevant search space and discards the ranges that will most likely not deliver the best solution. Thus, it can be beneficial when you have a large amount of data, or the learning is slow, or you want to minimize the tuning time. So in contrast to random or grid search, the Bayesian search keep track of past evaluation results, which they use to form a probabilistic model mapping the hyperparameters to a probability of a score on the objective function. And this is the official documentation of these HyperOpt package that I'm going to use. And this is a GitHub page. I definitely recommend you go through them. So what they're saying is HyperOpt's job is to find the best value of a scalar valued, possibly stochastic function over a set of possible arguments to that function. Whereas many optimization packages will assume that these inputs are drawn from a vector space, HyperOpt is different in that it encourages you to describe your search space in more detail by providing more information about where your function is defined and where you think the best values are. You allow algorithms in HyperOpt to search more efficiently. So the way to use HyperOpt is to describe the objective function to minimize the space over which to search, the database in which to store all the point evaluations of the search, and also the search algorithm to use. The most basic tutorial will walk you through they are giving some basic defining a function to minimize. So this is the important part, and we have already defined that. This is that objective function that will be minimized by HyperOpt. And that's what they're talking about. HyperOpt provides a few levels of increasing flexibility, complexity when it comes to specifying an objective function to minimize. The question to think about as a designer are, do you want to save additional information beyond the function return value? Blah, blah, blah. Okay, so the next few section, yeah, so this is the most common syntax of implementing HyperOpt. The simplest protocol for communication between HyperOpt's optimization algorithm and your objective function is that your objective function receives a valid point from the search space and returns the floating point loss, aka negative utility associated with that point. So I need to define this fmin. Then I need to define the space, algorithm, and max values. Okay, is there anything important, more important here? The trial object. Okay, this trial object we are also going to use to really see the purpose of the returning dictionary. Let's modify the objective function to return some more things and pass an explicit trials argument to fmin. Okay, so we have already imported this fmin, tpe, and hp. Yeah, let's just go and complete the function. So this is our trials, and now I'm going to define the fmin. So this space is the actual search space, and that will contain later when I am going to execute this function, I need to provide this space, and that will contain all the in neighbors, in components, minimum cluster size, etc. We will see that in a second. Let's complete the function first. I'm going to use TPE here. And what is this space eval? We already have imported it at the very top. This one, HyperOpt. From the package HyperOpt, we imported fmin, TPE, HP status OK, spatial eval, and trials. Print best. I'm also going to print some more thing. So, best trials. Result. Yeah, that should do. Well, I'm getting a syntax error. Let me see. I'm going to use generate cluster. This method, what does it return? Let me see again. In generate cluster, return me the clusters. So this is where we implement our UMap for actually doing the dimensionality reduction, and then I get my clusters with HDBSCAN, and that's what is returned in this generate cluster. So that's what I need. And for the arguments to this method, I have all of these message. Let's just copy them, and later I am going to change it down here. So message embeddings, that will become only embeddings here. In neighbors will become best params. Here, similarly in components, and the rest of all the things actually will be coming from best params. And what it will return is okay. With that, now I'm going back to, so this is my utils file. Now I'm going back to the main Jupyter notebook, and here I have already imported all the methods from the utils file, so I can. Now I'm going to define the H space. And what is H space? This is this parameter space. So Bayesian search takes this argument, and that's what I'm going to define over here like this. So I'm just doing hp.choice, and then in neighbors range 3 to 32, in components also range 3 to 32, and level lower, level upper, I'm just defining 10 and 100 respectively. And that HP is coming from the module from Hyperopt. So we have already imported HP from Hyperopt. Cool. And now I'm ready to do my Bayesian search method implementation. And that's this. Let's run these few cells because yeah, the Bayesian search is not defined. Did I made a mistake in Bayesian? And I just had to restart the kernel, and it ran just fine. So with this, my Bayesian search is now executed, and next I am going to print the sentences of a given cluster. Let's do for cluster 11. Or place best clusters. And these best clusters use obviously is coming from the output of the after running the Bayesian search, because that's what I get: best params use and best cluster use and trials use. I just have to pick all the intent from that particular cluster. All intent index. Okay, let's run this. Yeah, this is the result for this particular cluster, and obviously it is supposed to be a very long text because I'm getting all the text for this cluster number. List index out of range. Why did I get that? Let me fix. And I think I can just change these cluster number here to get rid of this problem. Yeah, so that's my all the text for this cluster. And the next thing I'm going to do is automatic cluster labeling. And for this purpose, for automatic cluster labeling, that is, we use Spacey library to get the words POS, that is parts of speech. From each cluster, we concatenate the most common verb, direct object, and top two nouns to build the cluster topic label. That's a core idea here. Now, this particular idea is coming from a rather recent research paper. Let me quickly open the paper. And this is a paper that I'm talking about. It was released in December 2001. Name of the paper is Open Intent Discovery Through Unsupervised Semantic Clustering and Dependency Parsing. So let's quickly go through the abstract. Intent understanding plays an important role in dialogue system and is typically formulated as a supervised learning problem. However, it is challenging and time consuming to design the intents for a new domain from scratch, which usually requires a lot of manual effort of domain experts. Okay, this paper present an unsupervised two-stage approach to discover intents and generate meaningful intent labels automatically from a collection of unlabeled utterances in a domain. So what they're saying is, in the second stage, the objective is to generate an intent label automatically for each cluster. We extract the action object pair from each utterance using a dependency parser and take the most frequent pair within each cluster. For example, book, restaurant. This is a single action object pair as a generated intent label. We empirically show that the proposed unsupervised approach can generate meaningful intent labels automatically and achieve high precision and recall in utterance clustering and intent discovery. So this is the core idea in this paper, and kind of that's what I'm going to use. The problem of unsupervised open intent discovery involves two tasks: automatically discovering the intents from a corpus of raw conversational data, and two, automatically assigning each utterance in the corpus to the discovered intent. We generate the intent label that are interpretable using the most frequent action object pair within each cluster. We found that the experimental results on the SNPs dataset are surprisingly good, where the discovered intents match with all ground truth intent labels, and the task of assigning each utterance to the appropriate intent achieves a high F1 score of 93%. The contribution of this paper are threefold. Anyway, so yeah, so that's the so what we need to build now is this action object pair, and following pretty much this underlying concept, and that's the core idea here. And what is to use the Spacey library to get the words parts of speech, and from each cluster we concatenate the most common verb, direct object, and top two nouns to build the cluster topic or cluster labels. So I need to import a couple of things. Let's close this. Yeah, and my data cluster will be data cluster will be a pandas data frame. So this is where I'm going to zip my all intent. Oh, here it is, intents and best cluster use. And I need to wrap these as a list. Okay. Label one. All right, so these are all the intents, that is all the text, and these are all the label st1. So let's quickly check. Data clustered. Yeah, so I was just checking a single label st1 equal to 2. Let's check another one, maybe 24. Yeah, looks all right. Okay, now next I'm going to find the IDF of every word. So inverse document frequency, or IDF, looks at how common or uncommon a word is amongst the corpus. IDF is calculated with this formula right here, where T, that is this single letter T, is a term or word we are looking to measure the commonness of, and N here is the number of documents, D is the corpus. The denominator is simply the number of documents in which the term T appears in. And the reason behind calculating the IDF in this case is that, as we discussed earlier, that we pick the most common verb, nouns, etc. to build the cluster labels. But sometimes the most common word or verb in a cluster is not the best choice. For example, for our this particular case where the dataset is Steam reviews, we will see the words play or game in most of the clusters or comments. To balance that, I use IDF part of the TF-IDF concept. If a word appears, the fundamental reason here is that if a word appears in all the clusters or all comments, it is probably not that important. Think of equivalence of stop words because they're everywhere. So, in contrast, if a word is not everywhere, we pay more attention to it, and that's the whole reason for doing IDF here. And later, when we look for the most common words, we give more weight to low frequency words and less weight to high frequency words, which have lower IDF score. And another point that I could have used the TF-IDF vectorizer function from sklearn, scikit-learn, but I did not use that in this case because the scikit-learn implementation includes some regex check, regular expression check within its function, which I do not want in this case because I pretty much here want to capture everything between two blank spaces, including all symbols or punctuations. And since later we will use a lemmatized and lower cased version of the words for cluster labels, I regenerate now the reviews with the lemmatized and lower case version of the words that we are interested in, that is verb, noun, adjectives, etc. We use this list. We will create a list here, and I'm going to name it as sentence with word lemma to find the IDF scores next. Oh, sorry, that is 4. So for the parts of speech tagging, I'm going to search for verb, noun, and adjectives. Or direct objects from the dependency. In that case, just append it to temp sentence. Lower and add a single space. Finally, add these temp sentence, or append this temp sentence to send with, sorry, send with word lemma. All right, let's quickly check our first 3 of them. And now I'm going to define the IDF method. I'm using this counter again. So counter in a single word, it's an unordered collection where elements and their respective counts are stored as a dictionary. And here I just need exactly that. That is, I need each of the element and their counts. We will see the result in a second. Documents. Update the word count with my word set. I'm also going to print. Okay, let's leave it for now. All right, next I need. I'm just going to print the word count. Okay. I need the total, which is a sum. Excuse me. Which is the sum of word count dot values. And now finally my word IDF. So this word IDF will be a dictionary whose keys are the words and the values are the IDF score. So that's the dictionary, and key will be let's actually first define what are key and the value. So for k, v, and okay, and inside I need to implement the log method, log formula kind of. This is the formula that I'm going to use. It will be slight changes on the denominator. So let's say log base 2 total divided by v. That is all. I need to pass send with word lemma. Print this word IDF. Okay, let's run this cell. Yeah, so that's the result of my word IDF. So actually it's just giving me for each of the words, it's giving me the IDF score. And later, why I need that? Because I want to give a different weights to different words. We will see that implementation in a second in the very next cell indeed. Yeah, so and let's also quickly check this word count here. I just want to see that if word count is what I want. Right. So this whole thing is my counter object. We can see it starts with this word counter, and this counter object, it's just a dictionary where each word and the number of times they appear. And we can obviously see these game, play, get, all these things are like the really high frequency words, because this is a review of games. So this particular word game in this particular exercise, in this particular case, is not too important because they pretty much appear in almost every comment, every review. So they are not that significant. And to capture these differences in significance of different words based on their frequency of appearance in the whole corpus, that's why I created this word IDF. Because a very high frequent word like game need to be given a very low weight in my model, because they are not significant, they're not very meaningful in this particular exercise. Okay, let's move on. So now back to our automatic cluster labeling, and as we discussed earlier, what we are going to do here is this. Here we will concatenate the most common verb, direct object, and top two nouns from each cluster for our automatic cluster labeling. So quite a few util functions here that first I'm going to write. I can actually write those in utils. Okay, forget it. I am just going to write it in the Jupyter Notebook itself. First one I'm going to write is a function to return documents of a single category. So this function will take a data frame and a category column and a category as 3 arguments and return me the documents of a single category. That single category will be df category column and that's this function. And the next function is to get the most common words in a list of words. And here again, I'm going to make use of the counter module. Collections.counter. To that you pass list. It will produce a dictionary with each item and also their value, their count, the number of counts as their values. So if for k in list, counter k equal to 1, that is, it appears only once, then I should ignore it, because in that case as well this is not significant. So just pass else counter k, multiply that with the IDF, multiply equal to word k. So this is where I'm making use of that weighting factor, or this is where I'm giving different weightages to different words. The basic idea is that if the word appears more than once in the entire cluster, repeat that word IDF times in our bag. If a word is a low frequency word, it has a high IDF value. So with this technique, we give more chance to this word to show up in the list of most common words. That's the very idea. Okay, so that's where I'm done, and I can return from counter dot most common. Yeah. All right, and now the last method in this regard, that is to implement automatic cluster labeling, is another function where I will be extracting labels from documents in the same cluster by concatenating most common verbs, objects, and nouns. Here we will concatenate the most common verb, direct object, and top two nouns from each cluster for our automatic cluster labeling. It will be a slightly longer function, but the function is rather very simple. We will see that in a second. Extract labels, and it will take category doc and another Boolean parameter. Let's name it print word counts equal to false. Okay, now I need to I'm just going to declare some variables here, that is few empty list and few empty string. Verbs, direct objects, noun, adjectives, all are list. Similarly, I have verb, direct object, noun 1, noun 2 as empty string. Now for each document, what I need to do is append verbs, direct objects, nouns, and adjectives to a running list for the whole cluster. So for I, category doc, let me put some documentation or doc string here. So these first argument, category doc, this is a list of documents all from the same category or cluster. So category doc is a list of strings like this: fun game, small amount, time unless, lifer, etc., etc., separated by comma, of course. So it's just a list of strings. And print word counts, this is a boolean as we discussed. True will print word counts of each type in the category. So here in this line where I am actually looping through the category doc, that means I'm looping through the each element, that is each of these strings within category doc. Okay. I can do like this because it's just a list. And then for is a stop word. Len of token. If this is greater than 0, only then everything will make sense, otherwise no point. Okay. So what I'm doing in this line is ignoring if it is a stop word or the length of the stripped token is less than 1. And if it is not, then all the below logic will make sense. Token the position. Extend. Lower, okay. So that was verb. Next is direct object. Token.lemma.lower. Yeah, this will kind of get repeated for the next one. So direct object is over. Next one is a verb. I can just copy this. Here. Next one and the last one is adjective. Yeah, cool. And at this point, if I just print these most common verbs and pass the number of words to be 1, I get the output like this. Actually, yeah, like this. So most common, as we remember, most common is this method that we wrote earlier, which will get me the most common words in a list of words. And the first, it takes the first argument is a list, and the second argument is a number of words, which is a number of top common words to return. And that's what I'm doing here from the verbs list, the most top common words to return, and that's a kind of output I get. Okay, what because I needed to see the structure of this output once again here for the next part of my code. And the next part is so right now I'm going to use this print word counts. Okay, now I just want to print this counter. And now let's take the most common words of each form. Yeah, so we saw the structure will be returned from the most common like this. So that means verb equal to I need to get the 0 and then 0 again. Okay, so I need to repeat this pattern a couple of times. Verbs and the objects, direct objects. The JS. Similarly, I need to do for noun 1 and noun 2. Yeah. Now concatenate the most common verb, direct objects, noun 1 and noun 2 if they exist. That's kind of the last step here. Label. J. I also need to concatenate the nouns, but I'm not going to concatenate all the nouns just like that. I need to run an if loop. That is, if the nouns are not already there in label words, only then concatenate them. So forward in label words. Only in that case. Finally, if join with an underscore. Return level. And now it's time to check the execution of the function, and I just put a random current category text as a list and run these extract labels, and this is what I get: aim time, game live. So what it's producing is the object action object pair from the phrases in each cluster as a cluster label. So like we said that these probably is not making much of sense because we are just picking randomly from the reviews. But just to give an example, the one that we discussed previously, that action object will be something like book, flight, so on. And that's following the paper's recommended technique of automatic cluster labeling with dependency parsing. And now I'm going to check the output from my get group method, and I will pass a data frame, category column, and a category and a label for this. So the df, the data frame, will be my df cluster that we already defined. Where is it? Yeah, that's the one. df cluster is our data frame that on which we are working currently. So this one has a text column and has a label st1 column. Okay, so that's what I'm going to use here. Get group. First, it will take the DAF clustered. Then the name of the column is label st1. Why it's saying oh, so this is data clustered, and the last one is just a single label randomly I'm choosing, and let's run it. Okay, so this one produces a data frame where I have all the label STs value as whatever I've given here, 18. So I need to convert it to a list. So let's do a list like this, and then pick only the text. Yes. So now I get only the text columns values as a list. So this is what I'm going to work with currently. All right. Now, yeah. So let's go on and check my next method, because right now the method that this is the final kind of method for this whole exercise, and this method will present the whole summary in a single data frame, and it will assign groups to original documents and provide group counts. So actually what I'm trying to do here, let's just something like this I'm trying to do. So I want to have all my label st values, their counts, and also the final topic or the main label of the entire reviews of each of these reviews. So for example, this is coming from this long method that we wrote implementing our automatic cluster labeling, that is extract labels. This method will do the automatic cluster labeling technique and give me the actual labels with action object kind of meaning, and that's what these column represent here. So this is the kind of output I want to see, and that's what I'm going to write a function for now. First, get all the unique numerical labels that was generated by the sentence transformer model. That means I have to apply, I have to get it from these data frame and applying unique method on this. And then create a dictionary of the numerical category to the generated label. So this is where I'm going to use the same thing that we just did. This list is what I need. So this will just produce a list of strings for a particular label. And the only thing I need to change in this expression is change this label st1 to, and because this is looping through each of the label names, so label values, so just label. Label dict, label. Extract labels. This is where I'm using my long extract label methods. Okay, with this loop, my label dict will be completely updated. Now I'm out of the loop, and so now I'm going to create a summary data frame of numerical labels and counts. Group by category call and then text dot count. Yeah. Text count. Sending equals false. Lastly, apply the generated labels. Label dict x. Now let's finally execute this method and produce the result. Data clustered. And that is it. That's the result that I got. So I got for each of the label, I got the final outcome of my topic model, and this is following the automatic cluster naming technique. So this is each of these labels, each of these topics actually are action object. That's how it is. And this column gives a count of each of these labels. So for 31 label, I have 50 count, and the 31 label is actually recommend game time. And once again, if you are not sure that what this automatic cluster technique is, we referred this paper that was published in 2021, which named Open Intent Discovery through Unsupervised Semantic Clustering and Dependency Parsing. And the main thought here is this, that the objective is to generate an intent label automatically for each cluster. We extract the action object pair from each utterance using a dependency parser and take the most frequent pair within each cluster, for example, book, restaurant, which is action and then object. And exactly we followed here. We took Spacy to do the dependency parsing and got the noun, verb, dependent objects, and then took the most frequent dependent objects, and then concatenated the noun, verbs, and the dependent objects, the direct objects, to form our labels. And that's what we see here. These final labels are the final topics, and they represent the action object as advised in the paper. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.